The surface of a liquid in a tube is often not completely flat. A meniscus is formed due to capillary action. Surface adhesion pulls a wetting liquid along the surface. This capillary action may cause a small pressure difference between the pressures of two immiscible liquids, capillary pressure. But even when this effect is small, it can be important because it kind of acts as a diffusive mechanism. Sharp transitions are smeared out, as you see over here. You don't have a sharp transition from only oil to only water. More on this follows later. In this video we will see how capillary pressure acts as a diffusion term, and we'll also encounter the so-called fractional flow function. So, how do we model that? We say, well, we have some pressure difference between the oil and water phase. Pc equals P non-wetting minus P wetting, and often the non-wetting phase is the oil phase and the wetting phase, the one which adheres to the grains, is the water phase. And then you have to model this somehow. So what's done, this is done phenomenologically, this is measured, and what people measure is that this capillary pressure can be modeled as a sigma, a surface tension, times square root of phi over k, times a water saturation, the normalized one, to some power law. Of course you then have to measure what your power is. Now, how can we use this? Now, this capillary pressure relates to water pressure and oil pressure. So we can use it to eliminate the oil pressure in terms of water pressure and a capillary pressure. A capillary pressure is then again modeled in terms of your SW. So that's what we are going to do. We get rid of our oil pressure, we have only one pressure left. So how do we do that? Well, we know there's C over here for water, and just combine K, KRW and mu W into one constant, lambda W, which is often called the mobility. So your volumetric water velocity equals minus lambda W times gradients of water pressure, and similarly for the oil pressure. And again, your total velocity is the sum of the two volumetric velocities. Okay, now we want to eliminate this oil pressure. How do we do that? We start with the total velocity. We write it as water velocity plus oil velocity. For oil velocity we use RC. And then we eliminate this oil pressure because we know the PO from here equals PC plus PW. So minus this gradient of PO gives you a minus gradient of PW minus gradients PC. Now, then we'd like to have here a lambda W, because then we have a lambda W times gradients PW, which is a water velocity. Well, we can do that. We turn this into a lambda W, but then we have to multiply by lambda O over lambda W. And now we see, hey, here we have a U water, and here we have another U water. So we have a U water times 1 plus lambda O over lambda W, minus this capillary pressure term. Let's simplify that a bit. Then we multiply, we turn the 1 into lambda W over lambda W, so we get lambda W plus lambda O over lambda W. We call that lambda total over lambda W, and we just leave the capillary pressure term as it is. And now we can solve for UW, because we see then that if we multiply by lambda W over lambda total, we get UW equals U total times lambda W over lambda total, and here also a lambda W over lambda total times lambda oil times this gradients of PC. So now we have expressed our water velocity in terms of mobilities, which are function of SW, so we know them, and in terms of U total, and this one again depends on SW. Now, we often use the concept of what's called fractional flow. I don't like that name too much, but okay, it's defined as lambda W over lambda total. So what happens if you use your FW? You get UW, this becomes an FW, so there we are. And then we notice that the gradient of PC depends on via SW on the spatial coordinates, so the gradient of PC becomes the dPc dsW times the gradient of SW, and add two minus signs. Okay, there we are. Why do we do that? Well, this term between the brackets is often called the capillary diffusion term. Because if you write it like this, you get UW equals your fractional flow times U total minus a capillary pressure term. Now about some interpretation. Well, in absence of capillary diffusion, UW equals fractional flow times U total. So that's where the name fractional flow function is coming from. It gives the fraction of the total flow attributed to the water phase. But this is only true in absence of capillary diffusion. So fractional flow is always defined as this, lambda W over lambda total, but it's only the fraction of the flow in case capillary diffusion is 0. Now, why do we call this term between brackets, why do we call it the diffusion coefficient? Well, if you later on include this into your mass balance, you will get a capillary diffusion times a second derivative of S with respect to X. So this will act as a diffusive mechanism. So that's why it's called capillary diffusion coefficient. So there we have our UW. Well, in a similar way you can compute U oil, because it's of course U total minus UW is, and then you use FW plus FO equals 1 to write it as FO times U total, and you use SW plus SO equals 1 to get this term over here. So in a similar way, you see the equations for UW and UO are very symmetric. So in a similar way, you can express the oil velocity in terms of a fractional flow function and the gauges of S0, SO. So this is how you can use your capillary pressure to express your water velocity in terms of total velocity, fractional flow, and capillary diffusion. And that's what we are going to use in our mass balances later on.